This is a related rates problem about a television camera and a rocket. So a television camera is positioned 4,000 feet from the base of a rocket launching pad. The angle of elevation of the camera has to change at the correct rate in order to keep the rocket in sight. Okay, so that's one thing that's changing. Also, the height of the rocket is changing because it's taking off. In addition, the autofocus of the camera has to take into account the increasing distance between the camera and the rocket. So that's another thing to keep track of, the distance between the camera and the rocket. We assume that the rocket rises vertically. And the first thing we're asked is to draw a picture of this scenario. So let's see, here's the ground. And then we've got a rocket that's taking off. And it's going to rise vertically. So it started off down there, but now it's rising up in the air. And then over here we have a camera, and the camera has to keep changing its angle to keep the rocket in sight. So we have this right triangle essentially. We know that this is a fixed 4,000 feet between the camera and the base of the rocket, but the height keeps changing and the distance, we'll call it x, between the camera and the rocket also keeps changing. As the rocket gets higher, that distance is going to become greater. When it was right here, it was a certain amount, and then it grows as the rocket grows. Also, there's an angle right here where the camera is having to, first it was just looking here, but then the angle starts increasing so that it can keep the rocket in its sight. Okay, so I think we have a pretty good picture of what's going on here. Here's the first real question that we get asked. Suppose that the rocket speed is 600 feet. At the instant, it has risen to 3,000 feet. Okay, so the speed isn't constant, but at least we know that when the rocket is 3,000 feet high, we do know its speed. How fast is the distance between the camera and the top of the rocket changing at that moment? Okay, so we talk about the things we know and the things we want. We'll start with what we want. When it says how fast is the distance between the camera and the top of the rocket changing, this is looking for how fast is this distance, x, changing. So we really want to know what dx dt is, but at a certain instant when the height is 3,000. We also know that at that moment, let's see, the rocket speed, so that's the change in height with respect to time, is 600. And have we used everything? The height is 3,000. The dh dt is 600. Yeah, we might have to find some other things out as we go along. So we want dx dt. We have dh dt. This problem is lending itself to this right triangle here, and since we're looking for some things related to the hypotenuse, we probably want to use the Pythagorean theorem. The Pythagorean theorem says that 4,000 squared plus h squared will equal x squared. So we'll take the derivative of both sides with respect to t. So d dt of the left side and the derivative with respect to time of the right side. So on the left side we get 4,000 squared just goes to 0. The derivative of that is 0, and we have 2h dh dt. So again, the derivative of this is just 0. It's just some constant being added on to the h squared. The derivative of h squared is the 2h from the power rule, and then dh dt because this is implicit differentiation. And then on the right side we have 2x dx dt. This is good because we pretty much know most of this information. We have the 2, the h is going to be 3,000, dh dt is 600. We don't know the x, and the dx dt is what we're searching for in this problem. But we can find this x even though we don't know it because we can use the Pythagorean theorem, which says this is 4,000. This height is changing, but at this instant it's 3,000. If we use the Pythagorean theorem, this squared plus this squared, the square root of that is actually 5,000. So x equals 5,000 at that instant. We've already taken the derivative, so this is a good time to plug in our known values. We really couldn't have done that before this point. We definitely don't want to put it in before we take the derivative. Any changeable quantity, you want to wait till after you've taken the derivative to put it in. So 2 times h, which is 3,000, dh dt is 600, equals 2 times x. We found out x is 5,000 with the Pythagorean theorem, and dx dt is the thing that we're looking for. If we solve all of this, we're just going to divide both sides by 2 times 5,000, which is 10,000. Those cancel. We have dx dt equals all of this. And when we calculate that, dx dt will equal 360 in its feet per second. So at that instant, this is how the distance between the camera and the rocket is changing. And the other question that we get asked in this scenario is, at what rate is the angle of inclination of the camera's line of sight increasing at the instant when the rocket is exactly 3,000 feet above the ground, traveling at 600 feet per second? So this data, the 3,000 and the 600, is the same as what it was in part B. But now we're not interested in dx dt, we're interested in d theta dt. How is the angle of elevation changing? So the things we know are pretty much the same story, but what we want is d theta. How is that angle changing with respect to time when h equals 3,000? And we still know that dh dt equals 600. Okay, so this time we need some formula that hopefully relates theta, this variable that we're interested in knowing how it changes, with maybe some h's, because we know we have some information about h. So this is h. And this is theta here. Is there a way to relate these two things somehow? Sure, you can use any of the sine functions. Well, cosine's not going to be super helpful because cosine is 4,000 over x. That totally ignores the h, so we don't want to use cosine. Sine would be opposite over hypotenuse. That would be an h over x. That's okay, but I mean, that's fine. But tangent is kind of sitting right there looking at us. The tangent of theta is opposite over adjacent. The reason I didn't use sine, I could have, is because sine of theta is h over x, and we don't, I guess we do know some things about x just from the previous problem, but tangent is really nice because one of the parts of it is a constant, and those are super nice to deal with. Okay, so let's use the formula. So we needed a formula that would relate theta to h, and tangent of theta, which equals h over 4,000. This is just tangent is opposite over adjacent. SOHCAHTOA, TOA, opposite over adjacent. Okay, this is awesome because now we can take the derivative with respect to time of both sides, and we will be able to find d theta dt. So the derivative with respect to time of the left and derivative with respect to time of the right is going to be, the derivative of tangent is secant squared theta, and then we have a d theta dt because it's implicit differentiation. On the right side, we have 1 over 4,000, and then the derivative of h, essentially, which is just dh dt. It's 1 times dh dt. Okay, so we know what dh dt is. It's 600. This is a constant, and this is the thing we're looking for, d theta dt. And then secant squared theta, that's something we can probably get. So secant theta here is the thing that we're going to have to kind of hunt around for, do a little bit of legwork to discover what that is. And at this point, we've taken the derivative with respect to time, so we can plug in specific values. We couldn't do it before because we never plug in changeable values before we take the derivative. But let's see, if we have theta, and this is a fixed 4,000, and at this instant, this is a 3,000, then, oh, and this is 5,000. We know that from the previous part. Secant is just 1 over cosine theta. This would be 1 over, let's see, cosine is adjacent over hypotenuse. So that's 4,000 over 5,000. If you have 1 divided by 4,000 over 5,000, this is just 5,000 over 4,000, or 5/4, or 1.25. Okay, that is secant theta, or 1 over cosine of theta. Okay, so we have 1.25 squared d theta dt equals 1 over 4,000, and dh dt is 600. If we do all of that arithmetic, we find out that d theta dt equals 0.096. The units are radians per second. So this is how the angle of the camera is changing with respect to time. This is not even required, but I always like to, I can think better in degrees than radians as far as a physical scenario. So if I looked at 0.096 radians and translate that to degrees, 180 degrees divided by pi, this will be about 5.5 degrees per second. So this camera, at the instant that the height is 3,000, is raising itself 5.5 degrees every second. Okay, so we found out d theta dt. We were asked for the difference in how the distance between the camera and the rocket was changing with respect to time. So these are two different rates, but they're related because they're all in the same scenario.